So I think this topic, we're really trying to get to the elephant in the room here, which is, when is this all going to happen? And in particular, there's a sort of wrinkle on that as well. It's not just when is it all going to happen. It's really what's the timeline look like from you reading papers in Science and Nature where people say, actually, this stuff is really working, to that turning into real application. So I think that's the kind of thing we're trying to get to. And you can argue a bit about what the definitions are of quantum advantage and what utility is and so on. But I think that's what we're trying to do. We're trying to get to some sort of estimates of timeframes. So Dorrit, I'd like to start with you because, well, firstly, tell us what you're doing at KEDMA, but also how you see this timeline in the coming years in terms of numbers and gates and qubits and so on.
Okay, so this timeline is really an interesting question because it's all about very weird definitions of quantum advantage, and everybody's talking about quantum advantage. It means something else, right? So we at KEDMA, what we do is we're trying to accelerate this timeline, and so you can think of the timeline as it seems like in the first step, the most interesting applications are going to be Hamiltonian simulations and physical simulations. And this is what we're going to see first, because that's only going to require not variational quantum algorithms and optimizations, but just simulations, running a single circuit and already getting some utility out of that. And we expect that with KEDMA's error and elimination software, which is what we do at KEDMA, we're going to be able to deliver that within the next year by basically running circuits of 1,000 gates or so. So this is what we do at KEDMA. We actually take a quantum circuit and we, by applying some software which applies error mitigation in a very efficient way, we enable running much larger quantum volumes than would be possible without that. So we expect the first quantum advantage, the initial quantum advantages, to happen in the next year already by reaching 1,500 quantum gates. But then the next step in the timeline is what's going to really affect also an interest, not only research centers but also enterprises, which is when we'll get to the ability of running quantum circuits on 100 qubits and more and 10,000 gates. And that will enable not only simulating physical systems on 50 qubits, but it will enable to do quantum algorithm design aided by a quantum computer. And this is something that not only researchers are interested in, but also enterprises. And this is something that we expect at KEDMA to enable already within the next 2 years. And the next step, that's sort of the most, what you call the elephant in the room. Well, if that elephant is here, we'll all be dancing around it. That's the ROI quantum advantage. And this we expect to be enabled when we will be able to run a few hundreds of thousands of gates or millions of gates. This was, the whole morning was talking about this. And we expect to enable that in the next 3 to 4 years, which is much faster than what it seems like these are the estimations. We think that we can go faster.
Thank you. It's interesting how people are more and more willing to put actual dates down now. So thank you very much for committing yourself in that way. Just to follow on from the previous speaker, you mentioned algorithm design as well. That is also an important step that needs to be taken. We shouldn't be focusing just on improving the fidelity of the hardware, should we?
Well, I think algorithm design, so depending on which algorithm design you mean, did you mean the actual quantum circuits, or did you mean the algorithms for applications of medical applications, etc.?
Just generally having I think I mean both, but it sounds as though there's too much of a focus on hardware and not enough on what we do with it later.
I think you're very, very right in that. I think that the hardware is progressing amazingly well, but what's really interesting is that with software, we can actually take a given quantum computer with a certain capability and make it capable of running much, much larger circuits using software, using algorithms. And this is what we do at KEDMA Quantum Computing. By the way, you're welcome to our booth outside to hear more about it. This is exactly what we do. We take the software and take a quantum, quantum hardware that can run maybe 100 of gates, and then make it be capable of running 100,000 gates.
Right. Okay. Oh, Ahmed has run away, but I'd like to. I'd like to come to
Sorry.
you next. He's just getting a glass of water. But the wonders of radio mics mean that you can tell us. So that we've just had one view of the timeline, and we saw the IBM roadmap on a slide earlier today. But what's your view of this timeline to practical applications? What do you think will happen when?
So from our side, will not be precise on date. From our side, we think that timeline really depends on many factors. One of them is timeline will be based on use case. It depends on the use case. So there is no exact date where we'll see quantum advantage. It depends on the use case. And even for every use case, the path to value will be maybe incremental before becoming disruptive. To give you some examples and be more precise, if we take the example of turbulence modeling for aerospace, we know this problem is complex and maybe we need error-corrected computer to solve it, but still is very important for aerospace. Is the number one use case for them. If we take other use cases which are more apply quantum heuristics for quantum chemistry or data classification, this maybe will happen before. So it depends.
So, okay, so it really depends on the application.
Yeah.
Scott, what's your take on this? And when we were talking the other day, you made an analogy with the early days of classical computing, where some specific scientific and military applications led the way. Can we expect that sort of scenario with quantum as well?
Most likely. So at Deloitte, we're a consultancy. Our goal is to understand what the hardware and software that others are building can do so that we can apply that to problems that our clients have. And our clients are typically the Fortune 5,000. If you think about that, what often happens is you have actually one of two problems. So businesses either have things they do one time, or more often they have things they do on a recurring basis. And the bar for value from a business perspective is slightly different in both of those cases. What's interesting, though, is if you sort of look at recurring use cases and where we might start seeing some of the first value, relative value of quantum, I think our current suspicions are that it's likely to be in the area of machine learning. It's likely to be in use cases where accuracy is more important than time to solution. And if you squint your eyes and sort of look around, you can see those kinds of things in insurance fraud detection, because case volumes are moderate and timeframes to evaluate fraud are reasonable, more so than credit card processing. So if you sort of look at where things might happen, and then if you ask when things might happen, I would say, if you believe the vendor roadmaps, that's probably somewhere in the 3-year-ish timeframes, and those roadmaps change all the time.
Striking though that people are saying 3 years and not 5 to 10 like they were 2 years ago. So I think that's progress. Millie, coming to you next. Perhaps you could tell us quickly what Noblest does, and then give us your take on this timeline to commercial utility.
Sure, absolutely. At Noblest, we're a nonprofit science and technology organization. Our mission is to solve complex and technical problems that benefit the public, as well as advance U.S. national security interests. And so, as a systems engineer, I will tell you that, I think of it in terms of, utility as it relates to the traditional classic ilities, if you will. And so I think we've heard a lot at this venue about improving quality, scalability, reliability, all of these things. If you think of one-to-one replacement of classical machines and quantum machines overtaking them, we'll need to see advancement in those areas. But I think, like Michio Kaku said, we're dealing with probabilities, not certainties. And so the good news is that there's a lot of advancement in error correction and improving, again, not just increasing the number of qubits for quantity's sake, but improving the quality through logical qubits and the other advancements in photonics that provide a lot of promise. I'd say that I think about what we're seeing right now in my company relative to AI acceleration. We were obviously looking at deploying hybrid environments where we're using, electronic processors, both CPU and GPU together. I think similarly, as quantum advances and as we realize the promise of photonic processors, you're going to see more practical applications evolve where you're using multiple computing implementations to solve problems and leveraging the benefits of all of those capabilities.
So by asking the question, when do the quantum computers start working, I'm sort of asking the wrong question, because it's actually, when does this become useful as part of a broader computing ecosystem? Is that what you're...
Yes, yes.
Okay, no, that makes total sense. And do you want to commit yourself to a timeline about when when this might be, and whether and what specific applications might be at the front of the queue?
Well, I think it's just like with any breakthroughs, right? It's oftentimes not just one singular technology that is the cause for that breakthrough. It's the convergence. And so I live in a world of convergence and integration of multiple technologies, and that's where we start to really see the value. Just as there was this long AI drought, and as hardware accelerated, as performance, made things possible for us to train our LLMs and neural networks, we're going to see the same type of thing with the convergence of multiple technologies together that will lead to those breakthrough advancements and timelines. But no, I will not quote a specific time frame.
No, fair enough. I like the analogy with AI a lot. Another technology that didn't work for a long time and then suddenly did. Although when you say suddenly did, I think ImageNet, and when they figured out about GPUs, so kind of 2009, 2010, and it feels like we're not quite there yet, but we're getting close. Lara, hello, all the way down there.
Yay.
So I think you're coming at this with a specific use case in mind, rather than when does it start working, but how can I solve this problem?
Correct.
And at the Cleveland Clinic, you have a collaboration with IBM, and you sent me this very interesting paper that was in JCTC about protein structure prediction. It was a very, very small piece of the Zika virus, wasn't it?
Yes.
So I just, what does that tell us about how close we're getting? I mean, it looks like a very impressive paper, and there are 4 rival systems, and I think the quantum system comes second out of the 4, and the machine learning system comes last, which is quite funny. What does that tell us about how close we are to this being useful?
Yes, I'm not going to give you a timeline. I
Okay.
know that question is coming. And what the paper tells us is that whatever the timeline is, we're going to be much closer to it when we work together. You just said, Tom, that you were encouraged by the fact that people on the stage are saying in 3 years or 5 instead of 10, like they used to a couple of years ago. And the way I see it is that is just what you would expect, because otherwise, if you commit to one time, you're basically assuming that getting there is purely driven by the current state of things, the current state of the technology, the current state of the community. But in quantum, it's very dynamic and conditions change along the way. What we have found in Cleveland Clinic through our partnership with IBM and partnership with other research institutions is that having a quantum computer on site, that's what we have. We have an Eagle machine with the 127 qubit. It is housed in the middle of our research institute, which houses 200 labs, 1,600 researchers, and that is right across the street from our main hospital in Cleveland. When you have that coalition of the doctors, right, who want to eventually use whatever you produce, the biomedical researchers that are working on answering the questions, and then the compute technology at its best and the science at its best, then you're much closer to working together and getting answers. The paper that you're referring to is one where we looked specifically, because of the limitations that quantum has now in its ability to simulate large molecules, we looked at the situation of rare diseases. Currently, modeling molecules related to rare diseases, or any disease really, is totally dependent on the AI algorithms that are out there. AlphaFold 2 was the platform that we used. And any AI algorithm, the output is as good as the input, right? And it needs large data sets. In rare diseases, there's just not as much to input. So then the output that you get with those machine learning approaches hasn't really been optimal. And that's why we decided that's a good use case for quantum. And this is just one example of how getting the use case right requires a lot of work. We have now 13 different projects going on with quantum. Each one of them took almost a year with back and forth between all those teams to come up with how to do it. And today we're announcing a new partnership that we're launching with the Hartree Center here in the UK that will be driven by the Cleveland Clinic in London. We're a global organization, and Cleveland Clinic in London, we're a hospital, it's in the Belgravia area, but it follows the Cleveland Clinic spirit, which is bringing innovation wherever we go, whether it is in providing care to patients, but also in research.
Okay, and we should say it was AlphaFold 2 that came last out of the 4 attempts to predict this structure of this particular bit of the Zika virus, and of course now we have AlphaFold 3, which is supposed to be a lot better. So we'll see. Doris,
And I'm sure it will do well. See, so that's the other point is that I don't really like to frame it as it is quantum versus.
right? Okay.
Right? Because when there is quantum pushing forward, we want the classical computing to push forward. And that is really how we will progress. And I don't see a future where we'll just be using quantum or just use AI. It's really whatever combination will give us the best answer.
Yeah, you're focused on solving the problem, not the specific technology. Dorothy, I wanted to come back to you on this question of speed versus accuracy, which Scott mentioned. How do you see? Is there how do you see that trade-off, and what does that mean for how we get to practical utility?
Hang on, because I said for machine learning. Some of this stuff, just to be really, it is the nuance becomes important.
Right.
Sorry, because what winds up happening is when we're looking for problems, what we're often trying to do today is displace what we're currently doing, and it's not just speed and trade-off. It's not a speed-time trade-off. It's that the cluster of problems that might be some of the first ones are machine learning where there is a quality time trade-off. But that's not necessarily true for optimization, and that's not necessarily true for chemistry. It happens to be true probably for some of the initial machine learning use cases.
Okay, so it depends on the application. But what's your take on this, Dorit?
Here, I'm not going to commit this time. So, but I do think that. So the thing is that, of course, we have to progress in both axes, and the more we progress, I mean, we get better and better, more accurate results with quantum computers. And the thing is that what's very surprising is that these algorithmic protocols that we can apply in order to improve the accuracy and the speed seem to only improve their benefit over just mundane techniques as the accuracy increases. So as we all know, when we get to more advanced applications, we will require higher and higher accuracy, especially for chemistry applications, but also for all other applications that we're talking about. And at least with our software at KIDMA, we see that the benefit that we are going to see using algorithmic applications is only going to be much more in terms of the circuit volume boost compared to what you can do without, what you can do with just bare applications barely applying the circuits without any error mitigation or error handling, with clever software techniques. So just I think it's very, very interesting to look at how we are going to handle errors in the future. So as we all know, error correction is one of the most important threads, and everybody's working on trying to get to fault tolerant quantum computation. And however, this is probably going to take more than 4 years in order to get to ROI quantum applications with just error correction. And error mitigation, as we all know, is very promising in the short run, but it's less promising in the longer run because it has exponential overheads. And what we do at KEDMA is we combine error correction and error mitigation. That's on our roadmap in the very near future. And this will enable both saving qubits and applying and getting to very, very high accuracies without such a large overhead in qubits and also saving on the speed. So this is why we are thinking of the timeline as something that, this is why I'm willing to commit that in 4 or 5 or so years, maybe not that committing, but 4 or 5 years, we'll get to something that's very interesting, because we will be able to get to highly accurate results using the error correction and error mitigation together.
Right. So again, so we need to think of those two as working together and not as, one as the gateway to the other. Imed, what other specific capabilities do we need that we don't have? I'm assuming IBM is not going to provide everything. So what are the other things that are outside your own roadmap that need to come together for this to happen?
In order to reach quantum advantage, we're already in quantum utility phase, as Jay said this morning from our side. On quantum advantage, there is capability linked to the quantum technology itself, and other capability linked more to the user. The capability linked to the technology are improving the hardware and software, which improving the performance, which is scale, speed, and quality, and reliability. So, and I think we are going there. So hardware and software side, I don't think it will be the bottleneck. The second capability linked to quantum technology is algorithms and algorithm discovery, which can be IBM. It needs to be all the community to find algorithm, either to find new one or improve the one that we have. When we talk about algorithm, one example, I think, of improvement is thinking about, someone talked about this morning, distributed quantum computing or parallelization of circuit instead of using a single circuit at a time. This is one capability. From the user perspective, I think, as Laura said, it's about collaboration. Finding the right use cases, there is no way anybody will find by himself. It's not IBM, it's the user to find the right use case, and also find the workflow and how quantum fits in a workflow. It's about classical and quantum. It's not classical against quantum. I think this is one capability. And the other one, capability relying on the classical side, is really the integration of quantum to classical. And this is not easy, like integrating HPC and quantum, or integrating quantum and making sure that this, let's assume if you're talking about fraud, you need to run it every day or whatever, and it needs, in the bank, there is some standard, and there is a lot of things that need to happen. And if you don't do that, quantum is useless. You need to integrate it in the real system and the real process.
Right. Okay. So there's quite a long laundry list there. Beyond the hardware, you need the talent, you need the collaboration, you need the algorithm design, and you need this integration. Well, speaking of integration, Scott, let me come back to you on that. Where do you see the if I waved a magic wand and we had a fault tolerant quantum computer, what bottleneck? Which of those are you most worried about?
Integration becomes actually the biggest one. No, I'm sorry. Talent becomes the biggest one. And the challenge is, if you think about it, today we have this thing we call data science. It takes people a couple of years to learn. I would submit we are very likely to find that we have a discipline called quantum information science, which also takes a couple of years for people to learn. That we will find we need a great number of quantum information scientists who are not currently in the pipeline. And if you remember back sort of a decade or so, there was a sort of a land rush for people who had data science talent. It would not be surprising to discover that in the coming years we have a similar rush for quantum information scientists.
Right. Okay. That's very interesting, because that goes back to what Peter Knight said right at the start about trying to build that pipeline now. Millie, is there a bit of of those other capabilities that we heard about? Is there one where that you think we need to be focusing more on? Would you agree it's talent?
I would agree it's talent. As a CEO, I would be lying to you if I didn't say I'm always looking to win the war on talent, and we can't win the war against our adversaries if we don't have a robust talent pipeline. And so, at Nobilis, we go to where the research is born. So we believe collaboration is a key element of that. Partnering with academic institutions, as well as growing our own talent from within, because it's not enough to just, hire from the outside. We learned, as Scott mentioned, through, with data scientists, we learned to grow our own. We like to say that we grow SMEs on trees, but, the quantum community is still relatively very small. And so I'm always looking to, invest in the best technology so that I can bring that technology to my researchers, to my principal investigators or basic applied scientists so that they can innovate. And without that, and without collaborating and working together with other nonprofits, with industry, we're just not going to get there. So I would say that's key. Technology in and of itself is not usually the hardest part. And I think, as Dr. Lara mentioned, getting different disciplines to work together in order to solve problems. I mean, we went through the same process of taking some of our aeronautical engineers, pairing them with our mathematicians to, at least in our first foray into quantum, look at, your more traditional flight optimization, path planning problems. And so it does require, intent. It does require diversity of thought, diversity of disciplines coming together to solve those problems that are going to get us over the hump.
Okay, and Lara, I'd like to give you the last word because you're unusual, I think, in that you're essentially you represent an end user organization that actually has a quantum computer today. So given that you actually have one, what are you finding is the constraint? Where does the bottleneck come beyond that? Is it talent? Is it algorithm design? Is it collaboration? Which one of those do you think is most constraining you beyond the hardware?
Well, it's really all of those. Right now, it's mostly culture, I would say.
Oh, okay.
So it's when we started in this journey, I have to deal with teams of biomedical researchers that are used to doing things their way. They're used to thinking about things their way, and then you put them with computer scientists and engineers who speak a completely different language, and you can't just expect them to work together. The analogy I always use, it was like having a room where half of it only speaks Chinese, the other only speaks German, and I'm asking them to give me a report in French, right? Like that doesn't really work, right? So getting, that's why it's not really like you push a button and then it happens. And having data scientists and quantum information scientists is still not going to cut it unless they are embedded in the teams. It's and technology. I know this will not go well in a room full of technology people, but technology is not a goal in and of itself, right? People didn't think that they could fly, but we do, right? We didn't think we could get to the moon, but we did. And there was a lot of technology that had to be developed along the way. None of that technology was developed because we wanted to develop it, right? The planes were not built because how do we build the best planes? They were built because we wanted to fly.
Right, technology is a means to an end. Absolutely.
It's a means to an end. That's why the use, it's more than the use case, it's the purpose.
Yep.
Why are we going there? And then if we focus on that, then we will build whatever technology needs to be built, including the quantum.
Great, thank you. That's a great place to leave it. Thank you very much. Please join me in thanking my panelists.
Thank you.